I'm Scott Hagstrom. I'm a professor here, director of the Wisconsin Center for Wildlife. Our office is right through that wall, and we've been coordinating the spring seminar series that we've had here this entire semester. I would like to say that this is the 5th seminar that we've been hosting this semester, and we were planning to have one more, but because of the new change that we have, the university essentially is shutting down because of the concerns about coronavirus. Dr. Perry Barbosa is not going to be doing a seminar next week like we had anticipated.
26th.
26th, that's right, skipping 1 week. But I know Jennifer is exploring some other options, perhaps through a webinar or something like that. We may be able to post to kind of wrap up that seminar series. But we've had a great time. It's been on the changing climate and natural resources with a focus on climate change. I just wanted to acknowledge the various sponsors associated with this seminar series, and if you could change the slide. We also, because it's a public gathering, we acknowledge the Ho-Chunk Nation and the Menominee Nation for their contributions. These are their ancestral lands where the University of Wisconsin-Stevens Point are located, and so we recognize their lands and their people. With that, I'd like to introduce Jennifer Summers, who's program development specialist for the Wisconsin Center for Wildlife, will be introducing our speaker.
Hello. First of all, I just want to say thank you for coming out despite the weather and everything. It's really great to see everybody here. So I would like to introduce our presenter tonight, Matthew Mitro. As a fisheries research scientist with the Office of Applied Science at the Wisconsin Department of Natural Resources. Based in Madison, Matt has been working with the DNR since 2003 on statewide fisheries issues with a focus on trout in Wisconsin's inland streams. Matt has also worked for the EPA's Atlantic Ecology Division and the Atlantic States Marine Fisheries Commission. He has earned his PhD in fisheries at Montana State University, studying rainbow trout recruitment. So without further ado, I would like to welcome Matt Mitro.
Okay, thanks. Wasn't set up.
How about I actually bring up your presentation for you?
Okay, thanks. So I was asked to come here and talk about coldwater fishes like brook trout and brown trout and climate change. And I would say climate change is an issue that many of us in the DNR have been aware of for a long time and concerned about for a long time and have been working on for a while as well. Back in, I think it was 2009, there was a collaborative effort started between the DNR and the University of Wisconsin called the Wisconsin Initiative on Climate Change Impacts. And we kind of got in on the ground floor of that effort to put together our first adaptive assessment for the state, kind of identifying the climate change concerns as to how they would affect natural resources in the state and what we can do in terms of adaptation. So I'll talk a bit about some of that work that started back then and has been ongoing since that time. When I do presentations on climate change and trout, I like to start with a map like this. So this is a map showing the native distribution of brook trout in North America. So brook trout is a salmonid that's native to Wisconsin streams. And on the map there, the area in green shows the native distribution in North America, and the yellow areas are areas where it's been introduced and become naturalized. But you can imagine that with climate change and warming, if we start to see a shift in that native distributional range of brook trout or a contraction of that range, Wisconsin might be out of luck. We're kind of on the edge of their native range there. Similar map for brown trout. Brown trout are not native to North America. They were introduced back in the 1800s. They become naturalized in our streams. They're a very popular sport fish in Wisconsin, so we manage these as well as brook trout. So, but again, they're kind of in the same range as brook trout. Changes in climate that would affect brook trout are likely going to affect brown trout as well. So we have trout in many different types of streams in the state. Across the northern part of the state that's forested, you'll see streams like the one up in the upper left here. Streams that may have a forested canopy shading them. We still have trout in some of our larger rivers. The picture on the upper right is the Namakagon River. You see mostly brown trout in the main stem of the Namakagon. You'll find brook trout in some of the headwaters or tributaries of the stream. And then on the lower right here is a typical stream in the driftless area of Wisconsin. This is a different type of habitat than you see across northern Wisconsin. Often streams are kind of outflowing through farmland or prairie type areas, you're not going to see trees or canopy in those streams. But they are very cold because of the abundance of cold groundwater in that part of the state. So this is a map showing our classified trout streams around the state of Wisconsin. So you can see how many of these streams are across the western part of the state, the driftless area, across the northern forested area, kind of an arm going from the southwest to the northeast, up by the Lake Superior Basin. These are streams that we have surveyed, anglers fish, we know there are trout in them. We've classified these. Class 1 streams are streams that typically support year-to-year survival and natural reproduction, so the trout in those streams sustain the fisheries in those streams. Class 2 streams might be somewhat degraded. There's typically survival from year to year. There may or may not be natural reproduction. And if there is, it's typically not enough to sustain a fishery. So we do often stock those streams to provide for sport fisheries for brook trout and brown trout. And then the class 3 streams are streams where you typically don't have year-to-year survival or natural reproduction. So they're very dependent on stocking, or they might be streams that are just seasonally used by trout. So this is the resource base we have. And one of the factors that kind of determines in which streams in the state you find trout is temperature. Temperature is very important. That's why we call these cold water fish, because they physiologically require cold water to live out their life cycles. Now, all fish in Wisconsin are going to be subjected to cold temperatures in the winter, but it's what happens during the summer that depends or kind of determines whether a stream community supports cold water fishes like trout or warm water fishes. When you do get temperatures that start to increase in the summer months, they can become stressful for trout in the lower graph here. And if they get hot enough, they can become lethal, and the fish simply can't live there. And those temperatures that are often stressful or lethal for trout in the summer are actually ideal for other fish like carp and the upper figure there. And then within that temperature range that are suitable for trout, you have optimal temperatures for feeding and for growth. So in our concern about climate change and how it might affect trout, we're interested in stream temperature and how stream temperatures may change. So one of the things we did was put together a map showing the thermal classification of all streams within the state of Wisconsin. And we did this as a modeling effort. We put together what was called an artificial neural network type model that predicts temperature time series during the summer months. And that's based on observations of stream temperature as an output for the model, and then inputs. There are variables that describe the characteristics of the stream channel, the watershed where the stream occurs, and then climate data, such as air temperature or precipitation. And then there's also a groundwater component to the model. So we use that to make predictions of what stream temperatures are to give us a kind of idea where our cold water habitat is for trout around the state. I color-coded these into cold, cold transition, warm transition, and warm. So the streams in which you'll find trout are typically going to be the cold streams. You'll typically only find cold water fish species like trout or sculpin there. And you'll find them in the cold transition streams as well. Those streams might be slightly warmer. You might on occasion see a warm water fish species like a green sunfish or some different minnow species, but they're typically trout streams. Then when they get further warmer, the kind of yellowish or orangish colored streams there, those are the warm transition streams. You might on occasion find a trout in those streams, but they're typically not what we think of as trout streams. You're more warm water fishes, and then the warm streams where you typically do not find trout. So this is the thermal resource base. So this is based on July mean temperature. So we take an average of temperature during the month of July. We see a lot of our cold water habitat along that western part of the state, the driftless area. Up in the Lake Superior Basin is particularly cold. You'll get some cold water across northern Wisconsin and the forested areas. When you get to the eastern part of the state, it tends to be a bit warmer. So this is what we have now. We then use these models to project how that distribution of thermal habitat can potentially change because of climate change, because of warming temperatures. And this was a project we did as part of the WICI, Wisconsin Initiative on Climate Change Impacts effort, in which we collaborated with the UW Center for Climatic Research at UW-Madison, where they took, the climatologists there took these different general circulation models that you see in the IPCC type reports, where they make projections of climate change across the globe. And what they did was they downscaled these to the scale of Wisconsin to make them somewhat more relevant to us here in the state. And we use those as part of our modeling effort. We did this for what was called the A1B Scenario. It's kind of a middle-of-the-road scenario that assumes continued use of fossil fuels and more carbon into the atmosphere. And we made projections for the mid-21st century. And this is what we found. So the map I showed you before is on the left, projections for the mid-century on the right. So you can probably quickly see that contraction of cold water habitat, a little bit less blue, a little bit less green. You'll see a lot more red showing up across the northern part of Wisconsin, the northern forested areas. So that would kind of suggest that streams in that area might be particularly vulnerable to climate change. Do want to stress that these are not predictions about what will happen because of climate change, but rather projections about what could happen under the assumptions of the model. So we don't know exactly how climate is going to unfold over the next half century. I think we might even be on track to being a little bit worse than the A1B scenario. But this kind of gives us an idea of that thermal habitat. So again, these are not all trout streams, but streams that have temperature, the blue and green temperature, streams that have temperatures that could be suitable for trout. So our next modeling effort was to look at fish distribution. This was kind of our ultimate goal as fisheries scientists. We wanted to see what's going to happen to our trout populations because of climate change. So this is color-coded a little bit different. So on the left is a kind of prediction about streams where it's probable that you would find brook trout today. So the darker the green is a higher probability that stream will support brook trout populations. And the darker the red, it's a lower probability that it would be suitable for trout. And I don't have the map up showing the streams of the state again, but it kind of follows the same pattern. A lot of that brook trout habitat along the western part of the state, Driftless area, across the north, and that kind of arm connecting them from the southwest to the northeast. When we look to the mid-century projections, the projections are not that good. They suggest fairly significant losses in trout habitat. Again, these are not the predictions and the projections are not necessarily saying that brook trout are in those streams, but just the likelihood that those streams would support trout. And so we're looking at a potential loss from current day 21,300 miles of streams where brook trout streams are suitable for supporting brook trout to about a 68% loss, down to about 6,800 miles of stream. Now, these are predicted for segments of stream, so it's a portion of the stream that goes from confluence to confluence. So if you have a tributary comes in, starts a new section, another tributary starts another section. There's of course error in models, and the predictions or projections for any one particular segment of the stream might have some error within them, but looking at it in a statewide perspective, it does give, I think, a pretty accurate depiction of where the habitat is now and how that habitat can change regionally in the coming mid-century. We put together another similar figure for brown trout. Not quite as many miles of brown trout stream as brook trout in the state, about 12,400 miles where they're present, or probability of being present today is high, and then a decrease of about 32% loss projected by mid-century. We'll add that there is some stream segments where there's predicted loss of brook trout might actually be more favorable for brown trout following that change in thermal habitat. It's not that brook trout and brown trout have different thermal tolerance limits, and I'll talk about that a little bit later, but that those optimal temperature ranges for feeding and growth slightly differ between brook trout and brown trout. So brown trout might be a little bit more tolerant of slightly warmer temperatures, and conditions may favor them a little bit more. So these are, pretty disturbing projections, losing 68% of our habitat for brook trout, 32% for brown trout. But I want to kind of put that in a little bit of perspective in terms of the quality of streams that we have today. So this is a figure I put together using data from the DNR's Fish and Habitat database. So these are data collected in streams from 2007 through 2014, catch per effort data. So our biologists go out, they do a survey on a stream, catch trout. This is looking at trout over 6 inches or greater in size. And this is showing the percentile streams that have that catch per effort compared to other streams. And what you'll see is a vast majority of our streams have very low catch per efforts. But then when you get to those higher percentile streams, it's quite literally off the chart. And those are some of our really good trout streams, our timber coulees or spring coulees or elk creeks or big brooks. Many of these streams that our anglers tend to go and fish. So I think looking at those maps, projections of stream loss because of loss of trout habitat, the ones you're likely to lose are probably more on the left side of this figure, those kind of streams that are somewhat marginal now. They're not our best trout streams. They may be somewhat marginal, thermally compromised a bit, likely the ones to lose. It's not to say that the higher density streams are not going to change in any way, but they're probably going to be a little bit more resilient. And the streams that many of the anglers target now for their great trout fisheries, probably the ones that are still going to be fairly good trout fisheries as conditions start to change. So I'm going to switch a little bit from climate projections and talk a little bit about stream temperature to kind of give you an idea of how stream temperature may change. And in particular, I want to use an example to show how air temperature interacts with precipitation and groundwater to kind of characterize what thermal conditions you would see in a stream. So this is some data from Big Spring Branch in Iowa County, a stream I'd worked on a number of years ago. This is in the southwestern part of the state, and it's one of our colder streams in the state. It's named after that quite big spring that pours out the side of a hillside into the stream. And I had a data logger in the stream measuring temperature about a couple hundred meters downstream of where that spring comes in. And so we put these data loggers in the streams. We set them to measure temperature every hour, and you can leave these in there throughout the year to look at how temperature varies over the course of a year. So this is data from 2010. This is somewhat of an average summer, not particularly hot. The green line on the graph here is showing air temperature over the summer. The blue line is the water temperature measured a couple hundred meters downstream from where the spring enters the stream. And then the black line on the bottom is a measure of water level. And what you'll notice is that when you see all these spikes in the black line for water level, those are the precipitation events. And what's happening is in this groundwater fed stream, you get these large precipitation events, you get this influx of surface water rushing into the stream. And that's much warmer than the cold groundwater. And you'll see whenever you get these spikes in precipitation, you get that spike in air temperature, or a spike in water temperature. And then I want to contrast that to another year. So this is 2 years later, 2012. So this was one of our hotter summers over the past decade. It was also one of the drier summers. We didn't really have any major precipitation events that summer, so that water level graph on the bottom is rather flat. And then you look at the water temperature, that remains rather flat too. So you have that cold groundwater coming into the stream. Despite the fact that you had these warmer air temperatures, you're not seeing that reflected in the water temperature in the stream. So the point of this is just to highlight the importance of cold groundwater to trout streams. So even though you're getting these warmer air temperatures, when you're in the stream relatively close to that groundwater source, as long as that groundwater coming out of the ground is cold, you're still having a cold water stream that will support trout. But when you get further away from that source of groundwater, then you start to see that influence of air temperature. So this is a similar map from 2012. I added that dashed line, blue line, and that shows up in the middle there. That's 2 kilometers downstream from that groundwater source. So as you get further away from where that groundwater comes in, then you start to see that air temperature having an effect on water temperature. And what I would expect to see as climate warms and we start seeing warmer summers, that cold thermal habitat in these streams might start to contract during those hot times of the year. So if we have a trout stream that has this much thermal habitat during relatively cooler summers, as summers tend to get hotter, that habitat might shrink and you might have somewhat less area of the stream to fish. Now I want to show you some trend data. So we're interested in what's happening with water temperature as climate changes. Are we seeing any trends in temperature in our streams? And one way to look at this is in terms of thermal tolerance limits. We put together this curve on the right here with data from Wisconsin and Michigan streams. And what we did was went out and surveyed streams for trout and measured temperature in those streams. And we measure temperature during the summer period, June, July, and August. These are hourly temperature readings throughout that time period. And to summarize them, we would look at different intervals of length. So it could be a daily average, it could be a 7-day average, up to a 63-day average. So taking every 63-day interval in that summer, averaging the temperature. and then out of all those, looking at the maximum that occurred, and then relating that to the presence or absence of trout. So if you go into another stream, measure temperature during the summer, calculate the average for any of these time periods, if your data point form falls to the left of this line on the graph, that's a stream where the temperatures are within the thermal tolerance range of trout. If it falls to the right of that graph, that's a thermally compromised stream. Temperatures are too warm. It's likely not going to support trout in that stream. When you look at long-term temperature data sets, probably the ones you're more familiar with seeing are air temperature. These are figures from, I think I got this from the NOAA website. We have pretty good measures of air temperature going back over the past century. We've reconstructed air temperature going many thousands of years further in the past. And you'll see this variability from year to year, fit a regression line to that to kind of identify what the trend is in that data set. So I'm going to show a couple of these for some Wisconsin streams. We unfortunately don't have such long time periods of temperature for streams. It was only in the maybe 1990s when the technology was kind of a little more prevalent and affordable to be able to put data loggers in streams to record temperature. One of the best data sets that I've worked with is actually a citizen science data set. So I got this from a person named Kent Johnson. He lives up in River Falls area, Wisconsin. And back in 1992, he's a Trout Unlimited member. He fishes for trout. He's very interested in water conditions in the Kinnickinnic River. 1992, he started recording water temperature in this river during the summer months. And he's kept that up over the past maybe 29 years or so. So this is a very long-term data set for stream temperature. And I have this data for 4 different sites on the Kinnickinnic River. So the Quarry Road site is upstream here on the map. The stream flows through River Falls, goes through 2 dams. Then you have the Upper Glen Park site. There's a Rocky Branch tributary, Coldwater tributary to the river, and then the Lower Glen Park on the Kinnickinnic. And this is what we've seen. So what I'm showing here are stream temperature measured at 4 different intervals. So I have the 7-day, 21-day, 42-day, and 63-day intervals. The dashed lines on here is the thermal tolerance limit for trout. And so ideally we want to see those stream temperatures remain below that thermal tolerance limit line and ideally not be increasing towards that line. These fitted lines here, I put these numbers on. That's simply the difference between the modeled temperature at this end compared to what it was at the start of the time series. So for that 7-day interval, we're seeing a little bit of cooling. The average temperature dropped a little over ½ degree Celsius over that 29-year time period. When you get to different intervals, 21-day, 42, 63-day, you start to see somewhat of an increase. And kind of see this pattern in some of our streams. You'll see it a little more pronounced in some of the other data I'll show you in a minute. And I think what's happening is it's not that we've been seeing necessarily hotter summers in terms of maximum daily temperatures, but our nighttime temperatures are not beginning as cool. And this is something the climatologists have been telling us we can expect in Wisconsin. So our nighttime temperatures are getting a little hotter and muggier. So whereas in the past we would get this nighttime cooling in air temperature and that would reflect a cooling in water temperature, we're not quite seeing that as much these days. So you would expect to see, as you start averaging the temperatures over longer time periods, like the 42-day, 63-day, that's when you'll start to see that increase occur. So this is for the Upper Glen Park site. Again, somewhat similar to the Quarry Road site. A little bit of cooling in the 7-day interval, longer intervals starting to show a little bit of warming. Things, oddly enough, were quite a bit more dramatic in that Coldwater tributary, the Rocky Branch. These temperatures are very cold. They're much lower than the thermal tolerance limit for trout, so we're not in any near-term danger of temperatures rising to the point where it's not suitable for trout in those streams. But there is much more of an increase that's been occurring over that time period. And then for the Lower Glen Park site, here we tend to see cooling. And that could be somewhat of a reflection of that Rocky Branch Coldwater stream coming in. So despite Rocky Branch temperature coming up a little bit, it probably does drop the temperature of the Kinnickinnic River a bit. So what's going on here? Climate's changing. We're seeing a lot of record-breaking temperatures. We're not seeing it in the streams, or at least in this stream here. Some of these stream temperatures I'm showing you are cold water streams. They're not, maybe are streams that are thermally marginal for trout. You might start to see more of this less influence of groundwater, more influence of surface water that's warmer. But one thing that I think is interesting is when you look at global air temperatures, so another map I found on the NOAA website, this is comparing temperature anomalies in this past year, 2019, compared to the 1981 to 2010 average. And the areas on this map that are blue, colder than average compared to the rest of the world, darker red, warmer. You see a lot of hot, warmer areas on the globe. The upper Midwest has been colder. So we've kind of, in a sense, lucked out in terms of air temperatures as far as trout streams go. We've been in somewhat of a cold spot. So if you walk out your door here in Wisconsin and look at air temperature and think it's not getting that hot, it actually has been not as hot as elsewhere on the earth. It's not to say it's always going to be like this. It hasn't always been like this, and it's likely not going to always be like this, but the past couple of years it has been, and that's probably what's reflecting those observations of cooling in some of our streams. I just have a couple more of these stream temperature data sets I want to show you. These are somewhat shorter. I haven't been collecting this data since 1992. I haven't been around that long, but I thought I would share it for some of the streams that I've been working on. This is Elk Creek, a Class 1 brown trout stream in Vernon County. And these are some of the data from the similar lengths of time period. So again, no obvious trend, not seeing anything bumping up against that thermal tolerance limit. This is a very high quality trout stream, cold temperatures. This is for Ash Creek. This is a brook trout and brown trout stream in Richland County. Again, somewhat similar data. Temperatures well within the thermal tolerance range for trout. And again, this is a very high quality trout stream, a lot of groundwater feeding this stream. No obvious trend, although looking somewhat cooler in the past couple of years, as we've seen in some other areas. And then the last one I'll show is Timber Coulee Creek. So this is in Vernon County. This was measured at the lower end of Timber Coulee. This is much bigger water. You're getting further away from the groundwater source. It's a wider stream, so you'll see somewhat higher temperatures. So again, within that thermal tolerance limit of trout, but getting closer as you get into this bigger water further away from the groundwater source. One thing I want to point out in here is what we've been seeing at this time period, 2012. So if you recall back in big spring figure I showed you, that was one of the warmer summers. We were seeing that in a number of different streams, and it showed up here in Timber Coulee. And if you look back at those NOAA maps showing temperature anomalies, this was one of those summers when the upper Midwest was relatively hot compared to other parts of the world. So it is kind of important as to what temperatures we're seeing globally and how it's occurring here in the upper Midwest as to what we're going to see in our streams. One interesting thing I want to talk about in terms of temperature, and I won't spend too much time on this, but I've talked about temperature in terms of thermal tolerance limits. If temperature gets too hot, fish simply can't tolerate it, they won't live there. But before temperature gets too hot, conditions in the stream can change. You may get slightly warmer temperatures that are within that thermal tolerance range for trout, but it could affect how species in the stream interact with one another. And this is an example with brook trout, brown trout, and a parasite called Salmonella edwardsii, or what anglers will commonly refer to as gill lice. So if you catch a brook trout and you flare open the gills and it's an infected fish, you may see these parasites hanging off the gills. Kind of look like little grains of rice hanging off the gills of these fish. This is a heavily infected fish. They're not always like that. Sometimes you might just see one or two. It's actually quite a prevalent parasite. You see it in a lot of streams around the state. And it was interesting in that this showed up in Ash Creek in 2010, and by 2012 it became an epizootic. And the conditions in the stream were such that we had this warmer winter, warmer spring, warmer summer. Temperatures in the spring were actually in Ash Creek were similar to what we typically see during the summer. Well suited for trout, but also well suited for the parasite's life cycle. So this parasite has a 30-day life cycle. Instead of having just a handful of cycles in a given year, you had many more cycles in a given year. So that probably led to more of these fish getting infected. And what was interesting is we found in this stream, a lot of younger year fish were getting infected. Typically you see the parasite on larger fish, but the prevalence and intensity of infections were getting so big in the stream that even younger year fish were getting infected. And you would often see some like this one up here where the parasite load was so heavy on the gills that the opercula were becoming deformed just to accommodate those parasites there. And whereas it's only a 5, 10, maybe 15 at the most on some of these younger fish, whereas some of the adult fish, we've seen up to 100 or more parasites on them. That body burden on these younger fish is much greater than it is on an older fish. And we were seeing this show up in a mortality effect on young year, and you would see this in the what we call stock recruitment data. So for a given stock size, under ideal conditions, you can have pretty good recruitment, a lot of young year fish being produced. We were able to show that in these, beginning in 2012, when that episodic occurred, we were getting this mortality effect on young year, and recruitment was just dropping. Brown trout do not get this parasite. It's a very specific parasite to brook trout, so that was great for brown trout, and that kind of led to them taking over in the stream as well. So just an example of how temperature changes, even though they're not in themselves lethal for fish, they can change how species in the stream interact with one another and can lead to losses in fish populations. So we have a lot of trout streams in the state. People like to fish them. We have some really great trout fishing right now. We're concerned about climate change. Conditions are changing. We've seen some mortality effects related to the parasite in some streams. We're concerned about warming. What's going to happen? Well, we kind of projected what could happen, but what can we do about it? And this is kind of where my agency is interested. There's a lot of things we do for trout management in the state, and we want to make sure that what we're doing is helping to build resilience into these streams, helping to protect populations that we have and make them less vulnerable to changes in climate. The fishing we have today is actually quite good compared to much of what we've had over the past century. And a lot of anglers would tell you we're actually in one of the golden ages of trout fishing in the state. And I point this out just to show an example of how we've been through losses of trout before and have built those populations back. And I think that some of the lessons from that work is informative as to what we can do to help build resilience today. So I drew this red line on here to highlight the portion of the state that's part of the driftless area in Wisconsin. So driftless area extends into Minnesota, Iowa, and Illinois, but I'll talk about Wisconsin here. And you see a lot of highlighted trout streams in this part of this state. This is one of those, actually has become a destination trout fishery in Wisconsin. A lot of people travel from Chicago, Twin Cities, from long distances to come fish here. Even people from out west, when the streams out west are being inundated with snow melt, they come here to Wisconsin to fish. But it hasn't always been that way. And even within many of our lifetimes, it wasn't. So this is a map of Wisconsin from 1975. So I found this in a Wisconsin Conservation Bulletin, DNR publication, and it was an article about trout stocking. I put the red line on there. That was not part of the original publication, but just to highlight that driftless area. And what this map was showing was the darker areas are areas of the state where there were wild trout populations, and they were less dependent on stocking. The unshaded counties, much of the southern part of the state, much of the driftless area, are areas where we did not have wild trout populations back in the 1970s. And the fisheries we had there were pretty much dependent on stocking. It's not like that today. We don't have to do hardly any stocking in the driftless area. So I want to talk a little bit about what happened. How did we get those fisheries back? It's actually quite an interesting success story. But first, how did we lose them? A lot of that was due to poor land use practices. So when people settled the area in the 1800s, early 1900s, many of them came from Northern Europe. They brought their agricultural practices with them that involved things like this, row cropping up and down hills. May have worked okay in Europe, given the soils they had there or the precipitation regimes they had, but we had different soils here. We have much more precipitation than they had. When you get rain pouring on these hills and running down, picking up speed, you get a lot of erosion. And what we would see sometimes looked like this. You would get these kind of head cuts forming, gullies turning into small canyons. Very significant losses of soil. So all the soil was being eroded from the land, deposited in the stream valleys, filling in these streams, streams becoming wider, shallower, warming up, no longer supporting trout. Fortunately, there were people back in the early part of the century that recognized this as a problem. And one of the nation's first watershed projects was actually started here in Wisconsin in the Coon Creek watershed. So this is just outside of La Crosse. And second in from the left, Dr. Hugh Bennett was I think he was appointed the first soil conservation director back at the time, led this effort along with Aldo Leopold from UW. And what they did was they worked with the landowners in these watersheds. They realized that it was a land use issue, it was how they were farming these areas, and to get people who live there involved in practicing conservation in their agricultural practices to kind of stem the tide of erosion. And I think they were successful in getting that started. We unfortunately still live with some of the legacy of that soil loss. If you go down into our stream valleys and coulee areas in the driftless area, sometimes you will see degraded stream banks like this. This may happen after these catastrophic floods that we get from that are thought to be related to climate change. These are one of the things we work on in our stream habitat development program in the DNR. If you fish for trout, you buy a trout stamp, that money goes to stream habitat projects addressing stream bank erosion like this. I want to quickly run through a list of all the things that we did over the past few decades, or 5 or 6 decades or so, that kind of led to this resurgence of these wild trout fisheries in Wisconsin. In the around the 1970 area, we were, I guess, lucky in a sense to have, although we did improve our agricultural practices, there was a change in precipitation regime. And this led to improved base flow in streams. So we were seeing more flow, more water in the streams, which is beneficial to trout. We had our stream habitat development program. Again, the trout stamp money for stream habitat work started in the mid-1970s. Some of this work in the 1980s involved what we call lunker structures. So this is creating kind of an artificial undercut bank, which are found to be provide some really phenomenal habitat for adult fish, led to these really high densities of trout in some of these streams. The Farm Bill in 1985 was very important, instituted cross compliance. If you were a farmer and you received agricultural subsidies, you were required to have a conservation tillage or conservation tillage type plan to address soil erosion. CRP, Conservation Reserve Program, paying farmers to not farm on some of their more vulnerable lands. This is very important for helping to not only cut back on soil erosion, but to get more infiltration and recharge into the groundwater, which kind of provides that cold water for these streams. And then the wild trout stocking program. This was started in the 1990s. Most of our stocking up to that point had been from domestic broodstock and hatcheries. So these are fish that have lived many generations in hatcheries, and they became well adapted to live in hatcheries, not so much for streams. What we started doing was getting eggs from wild fish and then raising them in the hatchery to a young age and then stocking them. So these are fish only one generation removed from the wild, having much better survival rates, and this showed up in making it much easier to reestablish wild populations, leading to some of these fantastic fisheries that we have today in our driftless area streams. So I want to finish up by kind of hitting on some of these adaptation strategies, and I'll start with the stream restoration work that we've been doing. And again, a lot of this work involves sometimes getting heavy machinery in there, streams that have become degraded, wide, shallow, oftentimes because of certain types of tree species that live along streams like box elder or tag alder that kind of don't hold the banks together very well and lead to a kind of bank destabilization and widening. Getting in there and narrowing these stream channels, helping make the stream channels deeper, keeping that cold water cold as it flows downstream. I want to highlight a few recent projects related to stream habitat restoration in terms of kind of building in resilience to climate change. This one is for the Hunting River in Langland County. Dave Seibel and Taylor Kern from Wisconsin DNR have been involved in this effort. And what they did on this stream, this was a stream that was kind of encroached by tag alder. Tag alder kind of, again, one of those tree species that doesn't do well in holding banks together. They debrushed them back, they narrowed the stream channel, they put some woody debris into the streams to help create structure for fish. And in the coming year, they're planning on some of these kind of open point areas, planting some native tree species back in there to help kind of rebuild the canopy and help shade these areas of the stream. Another one, this is from work that Dan Oley has been doing in Dane County on Sugar River and Black Earth Creek, involving planting trees, again, to get a canopy back and provide shading for some of these streams that are becoming warmer. On the Sugar River, they've already planted 75 trees on one of our state fishery areas. And on Black Earth Creek, this coming spring, they're already scheduled to plant 200 more trees, or 200 trees on this Black Earth fishery area near Highway KP in Dane County. West Branch of the White River in Waushara County, some work that Sean Sullivan and one of our habitat specialists is doing there. This is kind of interesting in that kind of the climate change angle has been some disease and pest issues with trees. In this heavily forested area, there was a lot of oak and ash. And oak wilt is a disease that's been affecting oak trees that's been moving north, presumably because of changes in climate. Really hit the oak trees heavily in this area, and then the emerald ash borer hitting the ash trees. And whereas wood in streams can be a good thing, this was a case of too much of a good thing. So there was just a lot of dead trees falling into the stream at once. The figure on the upper left kind of shows that, although I was told there are many areas are much worse than that. And what it was doing is trapping sediments and completely disrupting the sediment dynamics in the stream. You were losing gravel substrate that the trout need for spawning. So their project involved getting a lot of this wood out of the stream, although leaving some, and opening up that stream channel again, getting some of that gravel back to help support trout reproduction. And then the last one I'll show is up in Douglas County, up near Lake Superior. Here a big issue is culverts. There's a lot of roads that cross these streams, and oftentimes the culverts that are put in are not of sufficient size to handle the precipitation events that we're getting now. This particular stream, that's a kind of a before picture from some of the original culverts. They're rather small, and they were getting precipitation events, and this happened multiple times over the past decade where the road just got completely blown out. So they were finally got some funding in to kind of replace this and make a bigger culvert that could better handle some of the precipitation and flows that they're getting or seeing more frequently now. Just a few other things involved that can be important for improving resilience in streams. This is an effort that I've been involved in. It's a national fish habitat partnership called Fishers and Farmers Fish Habitat Partnership for the Upper Mississippi River Basin. And this covers Mississippi River Basin portions of Wisconsin, Minnesota, Iowa, Illinois, and Missouri. And what we do is we provide funding and support for projects that help fish and streams, but also benefit farmers. And the idea being that agriculture is a big part of our landscape, and if we're going to make any changes in how we live on our landscape and be able to build resilience into climate change into our streams, we need to work in cooperation with the people who live and work there. So this is work as far as our fish habitat partnership. It's not just resource agency people like me, but it's also people representing farmers. There are people from the associations like Minnesota Corn Growers, Iowa Soybean Association, farmers here in Wisconsin involved. One of the projects that we funded in Wisconsin is related to something called Prairie Strips. So this is a concept that came out of Iowa. The idea being that if you have a big farm where you're doing row cropping, you can strategically plant restore prairie in certain portions of your farm, and this has been shown to significantly reduce overland flows and erosion and soil loss. So again, something that can help benefit farms and streams and fish health as well. One other farming issue I want to point out is related to rotational grazing. This is something you're starting to see more of in the driftless area. And if you go shopping and you like to eat beef, you'll often see sold as grass-fed beef. And this is often coming from these rotational grazing operations. I kind of like this quote from one of my colleagues, Dave Buchano, retired recently, essentially saying if we can get more farmers into this grass-based farming, a lot of our problems and concerns can be solved. Things like erosion, manure, pesticide, herbicide runoff, overgrazing. And we've seen this. Dave's up in the middle of that picture there. On the right is Rod Ofty. He's actually a farmer on Fishers and Farmers partnership with me. I know him through there. And he also owns this operation on a rotational grazing operation on Spring Coulee Creek. Again, one of our phenomenal trout streams in the state. Very high brown trout densities in that stream. And an area where he does rotational grazing with cattle in that area. You don't have erosion problems there because of farming, and you don't have the pesticide runoff, herbicide runoff, manure issues. And it works really well in parts of the state like the driftless area, and you're starting to see more of that. couple more things I want to highlight is public participation in terms of how we manage resources in the state. Many of you probably have heard of the Conservation Congress and the meetings that we have in the spring, where anglers and hunters and anyone who's interested in how we manage natural resources in the state can participate and kind of lend their voice, vote on issues pertaining to hunting, angling regulations, or even different resolutions related to how we manage resources or how we deal with even issues like climate change. I kind of like this article I found in an old hunting and fishing magazine from 1942, and this is describing the whole process that we still have here today in Wisconsin. And this was written about 9 years after it started from the, I think one of the first directors of the Wisconsin Conservation Department, H. McKenzie. And again, this is a process whereby anyone in the state who's interested in natural resources can kind of lend their voice to the process. So this is coming up in April. These spring hearings are held in every county. You can attend the hearing itself to participate. And I think last year we started doing this online, so you can even participate online, either by voting on issues that come up during that spring hearing, or if there's something of concern to you that you want to raise, you can work through the Conservation Congress to raise those issues and put them up for a vote for other people in the state to consider. Public participation is also very important in forming management plans for resources. We recently completed a trout management plan for the state of Wisconsin, and you'll find in this plan, well, one thing I want to point out, climate change. We, of course, as scientists and biologists, were concerned about that, but more importantly to us in forming this plan, we worked with a stakeholder group from different people from different walks of life around the state to hear from them what's important to them. And climate change was one of the top issues that they highlighted. And it was very helpful to us to have that public support for addressing issues like climate change. And so that shows up in this plan. And one of the action items that we're going to be working on in the near future is this concept called brook trout reserves. And it's simply an idea to identify kind of those best brook trout areas that we have in the state today, areas that are really worth protecting, really worth investing our resources in to protect them. So you'll be hearing more about this in the coming years. And again, it's not in any way meant to limit how you access or fish for brook trout, but simply how we direct our resources to them, so that we are not wasting our money on areas that are going to be very susceptible to loss because of climate change, but rather putting them in areas where we can kind of realize that benefit. Two more items I want to cover. One, also related, probably seen in the trout management plan, related to genetics in brook trout. There's been a lot of work here out of Stevens Point from Brian Sloss, Wes Larson, many of the people who worked in their labs related to genetics in brook trout. There's been many advances in genetics and genomics, and we've really learned a lot about the genetics that we have in brook trout in Wisconsin streams. As it turns out, we've done a lot of stocking over the years, and many of them came from domestic sources. And many of our wild populations, streams that we don't stock, haven't been stocked in years, actually do have genetics, domestic genetics in them. So their genetic diversity is kind of low. This could potentially be an issue, and when you ideally want greater diversity in the genetics in the population, so that when you do have changes in environmental conditions, maybe some of them will be better able to withstand those conditions or adapt to them. So we'll be working on reintroducing native genetics into some of our wild populations that have domestic genetics in them. So this is an effort that we'll be studying in the coming years. And the last thing I want to talk about is future generations of anglers. If we're going to protect these fishery resources, we really need people to care about them. And we need future generations to care about them. We have sometimes do creel surveys on streams, and we did one on Timber Coulee Creek back in 2008, and we repeated it in 2016. And over that 8-year time period, the average age of the angler fishing Timber Coulee Creek increased 8 years. So it's just that one group of anglers that's kind of aging through. And that's concerning to a lot of resource agencies around the country, that we're not getting new recruitment of new people concerned about fisheries and wildlife resources. So take a kid fishing, take a friend fishing, get people aware of these resources, and hopefully they'll learn to value them, and that'll be very helpful to helping get people to do the work we need to do to protect these. So with that, I'll just leave these acknowledgements up here for many of the people who contributed to a lot of this work. And if there's time, I'd be happy to answer any questions. Oh.
We'll take a few minutes for questions.
Yep.
Do factory farms have any problems or things that you use or not use?
Do factory farms have any problems for
For your work.
work? Probably do. I haven't worked on any specific projects related to factory farms. I know, probably one of the main issues of factory farms is the manure and the waste disposal issue. And that's certainly been an issue on many of our streams. A lot of the, what do you do with the manure? A lot of times it's spread over farms and you get an ill-timed precipitation event and it winds up in our streams, and we've lost a lot of trout populations because of that. So I would say, yes, it is an issue.
You spoke about rotational grazing, and the photos you had cattle in the streams.
Right.
I remember once upon a time it was all the rage to fence cattle out of streams.
Yep.
But recently I've either heard or read that it's okay to have cattle in streams. Which way is it?
It's probably a scale issue, and maybe it's regionally dependent too. It's probably not the most representative picture of that farm, because that was the only time I've been there where I actually saw the cattle walking in the stream. They do have off-stream water sources that they can use, so they don't necessarily always go in the stream there. But with the rotational grazing, the density of cattle in the area is very low compared to maybe what you've historically seen in some places or what you see out in the West, where it is a big issue when you get too many cattle in streams. So I would say a scale issue. Some not necessarily detrimental, whereas if you're having stampedes going through, maybe that's going to be a problem.
Your graph showing the relationship between stream temperature and precipitation events was pretty striking. And I imagine urbanization or development would exacerbate that. Is there, have you done any analysis to figure out which streams are not only threatened by climate change, but that urbanization might be an area of concern as well?
Yeah, that's a good question. Some of my colleagues had done some of that work years ago, in one sense looking at level of urbanization related to stream temperature. So as you mentioned, one of the issues is when you get precipitation events and it falls on hot asphalt or concrete, and that can warm that temperatures up in the stream. So it really depends on how much urbanization you have in the watershed. I think the one study I saw put it at about 11%. When you get more than 11% of a watershed having impermeable surfaces, you start to see changes in groundwater temperatures and stream temperatures. So it kind of hits streams both ways. One, surface runoff from those hot surfaces during the summer, and then if you have less groundwater infiltration to less groundwater recharge. There has been some work in terms of what's called land transformation models, so kind of looking at how urbanization may change based on human demographics in coming years. So that work has been done too.
You talk about dam removal. For example, on the Prairie River, they removed the Prairie Dells Dam, which probably lowered the temperature below it, but it put a lot of sand in the river. So have you had some experience with that issue?
I have not personally had much experience with that issue. I know dam removal has been a big issue of concern. I know some people who do work on that. That is I guess an issue. When you do remove these dams, you have that sediment load that's been trapped that comes in the stream. It does come into play in beaver dam removal. We've had some streams that have been historically inundated with beaver for many years, and it traps a lot of sediments. And I've seen some of them, pictures of them pulled out, and just an immense amount of silt and mud and muck. It's an issue, but sometimes nature helps take care of it when you do get heavier precipitation events to kind of work that sediment through and ideally change the dynamics so you're not having that repeat again. But Yep.
You mentioned 11% impermeable surfaces in relation to this gentleman's question.
Mhm.
Does that include things like house roofs? Yeah.
I believe it does, yeah.
I think we're about out of time, so thank you for coming.
Okay.